Buenos dias. I'm sorry, but that's all what I can do in Spanish. My company, BIS Vakuumtechnik, was founded by my father, Christoph Wils, in 1979. He was employed at a big producer of vacuum pumps in Germany, in Cologne. And he was responsible for selling vacuum pumps in the packaging market. And he made the patent for a centralized vacuum system. And his boss told him, okay, Mr. Bills, well done, but we do not like this because we are a producer, a manufacturer of vacuum pumps, and we want to sell vacuum pumps. And with a centralized vacuum system, the customer needs less pumps. And therefore, we don't want to use this patent. My father was a little bit disappointed. He left the company and founded his own company, BIS Vakuumtechnik. Today, I am the general manager. I have made an apprenticeship in a physical lab. I worked there in a lab for high vacuum technology for 6 years. And beside this, I passed the night school, and afterwards I studied physics. And you see the three guys there on the almost white side. This is my son. He is now for 2 years also in the company. We are located in Hennef. This is in the area of Cologne, nearly in the middle of Germany. We are working with approximately 20 workers up to now. We are focused on vacuum technology in food industry. Vacuum technology or vacuum is used in a wide range in all over the industry, but only in the small part, the packing industry, that's where we are working, where we are focused on. That is to say, we project, we build and make maintenance for central vacuum systems. We repair and overhaul vacuum pumps. We have an own lab for the calibration of vacuum meters. And we make package testers, small testers where you can check if your package is tight or not. But most of all, we are specialized in central vacuum supplies. We have made more than 350 big installations of central vacuum supplies, most of them in Germany, of course, but nearly all over the world. Okay, vacuum supply for packing machines. That's what we want to talk about today. This is a well-known packing machine, a so-called thermoformer. And for this thermoforming machine, we need vacuum. First, we need vacuum at the forming station, where the film is formed. Normally, the pressure for the forming of a foil is between 100 and 300 millibar. It's depending on the type of foil and on the thickness of the foil. Furthermore, we need vacuum for the sealing station, where the package is evacuated and afterwards it's sealed. Typical final pressure is between 2 and 20 millibar, depending on the product and on the type of package. Why do we need vacuum? We need vacuum because of the lifetime of the product. Because if you have on the food, you have bacteria. And the growth of bacteria is depending on oxygen. And therefore, we have to reduce the oxygen in the package. We can do this by evacuating the package and sealing. We have a vacuum package. Or we can make a MIP, a modified atmosphere package. That is to say, evacuate to a pre-selected final pressure, and then regas with any gas like nitrogen or CO2. So we want to decrease the residual oxygen. But what does it mean? Or how can we calculate the residual oxygen in a package, in an MIP? Air is a compound of nitrogen, oxygen, and some other gases like noble gases. And approximately 21% of the gas in the atmosphere is oxygen. If you now make an MIP evacuating and regassing with CO2 and nitrogen, the concentration of oxygen in the package afterwards can be calculated with this equation. The concentration of oxygen is the reached final pressure during the evacuation process divided by the pressure after regassing multiplied with 21%. So the CO2 is the concentration of oxygen in the package, PE, the reached final pressure, and PG, the reached pressure after regassing. Let's make an example. In the packing machine, we evacuate the sealing chamber down to 2 millibar and regas with a combination of CO2 and nitrogen up to 1100 millibar. So the residual concentration of oxygen in the package is 0.04%. This is under the condition if there is no gas flow through the foil and there is no degassing or engaging of oxygen in the product, because a lot of products are known that they will degas oxygen. Another example, now we evacuate once again to 2 millibar, but now we're gassing only up to 800 millibar, not 11 than before. And now the concentration of oxygen is only 0.05%. So this is very important. The residual oxygen concentration in a package is depending on the final pressure during evacuation, but also on the pressure reached with the regassing of the sealing chamber. Mostly used is regassing up to 1000 millibar. So the residual oxygen is the final pressure multiplied with 0.02 in percent. And so normally, if we want to reach a residual oxygen concentration lower than 0.1%, we need a final pressure of minimum 5 millibar in the package. Okay, normally the vacuum pump is built in the packing machine. We have the vacuum pump in the packing machine. Here is shown the pressure in the sealing chamber depending on the time. We are starting here at 1000 millibar. The vacuum valve is opened. The pressure goes down first very fast, and then we need more and more time to reach the desired final pressure. This is a physical process. This curve is a so-called E function. It is in physics, it is a well-known function. It is known in electricity if you are charging or decharging a condenser. It is known for a lot of things in physics. The pressure after the time t is given by the starting pressure, normally atmospheric pressure, multiplied with E, the so-called number of Euler, up to minus S over V multiplied with T. P is the pressure in the chamber, P0, the starting pressure. S, this is the pumping speed of the vacuum pump, of the installed pump, here. And V is the volume of the chamber. So with this equation, it is very easy to calculate what is the required pumping speed, or what is the time we need to reach a desired pressure. But that's not true, because this equation is only usable if the pumping speed of the vacuum pump is always the same, is constant with the pressure. And later on, we will see this is not. So therefore, the calculation of evacuation is a little bit more complicated. Okay, the vacuum pump is in the machine. the vacuum pump is not without any problem. The vacuum pump will make noise. It will make heat. And if you have a normal rotary vane pump, the total power draw of the vacuum pump is transferred into heat. And this in a cooled, hygienic room. Sorry. And next point is the hygienic aspect. The pump is oil lubricated. So we have the danger of contamination oil to the fresh product. We have a disrupted energy balance because the room is cooled. We have to cool down the heat load from the vacuum pump. And next point, if the pump fails, or if you need to make maintenance at the pump, you have to stop the whole packing line till the pump is repaired or removed. So therefore, there are some good reasons to remove this vacuum pump out from the hygienic area where fresh products, cooled products are packed. What will happen if we remove the vacuum pump? The vacuum pump is out of the hygienic room, and we have a pipe between the pump and the packing machine. And now let's have a look again to the E function. First, the pressure drops down a little bit. The pipe is pre-evacuated by the vacuum pump, and now the vacuum valves opened, and then we have a very fast pressure equation between the chamber and the pre-evacuated pipe. Therefore, the pressure drops down, let's say from 1000 millibar maybe to 850 millibar. But now the vacuum pump has to evacuate the volume of the chamber through the small pipe. That means we need much more time to reach the desired final pressure. So it's the same. My wife is...
So please, I have one question.
Yes, please.
Can we calculate what is the relation between the distance between the pump and the machine and the time that we lost with this distance? Is it possible to calculate it?
Yes and no.
Okay.
I will show you in a few minutes.
Okay, perfect. Thank you.
You're welcome. So the small pipe between the vacuum pump and the sealing chamber is the same like it's true. I will receive every evening from my wife 1 bottle of beer and a 5-meter long small hose to avoid that I may ask for the next bottle. That is to say, we have the flow resistance of the pipe. And the flow resistance, and now back to your question, the flow resistance of the pipe is depending on the length of the pipe, it's depending on the pressure, and it's depending on the diameter up to 4. And that's the point. The diameter up to 4 means if I decrease the diameter to the half, let's say from 100 millimeter to 50 millimeter, the flow resistance go up 16 times. And that's the problem. So back to your question, it is possible, of course, it's possible to calculate, but it is not so easy because the flow resistance is also depending on the pressure, and the pressure changes during the evacuation. So it is possible, but not so easy. So that is to say, the effective pumping speed at the packing machine is depending on the pumping speed of the vacuum pump and on the conductance. And the conductance of a pipe is 1 over the flow resistance. What does this mean? I have prepared a curve. Here you see the effective pumping speed at the sealing chamber divided by the pumping speed of the vacuum pump. That is to say, this is the efficiency of the vacuum pump. And here we have the pumping speed divided by the conductance on the pipe. What does this curve show? It shows if the conductance of the pipe is the same like the pumping speed of the pump. Let's say we have a vacuum pump, 300 cubic meter per hour, and we have a pipe with a conductance of 300 cubic meter per hour. Should be more than enough? No, because now S over L is 1, and so the effective pumping speed is only 50%. So vacuum pump, 300 cubic meter per hour, and a pipe with a conductance of 300 cubic meter per hour. That means we have, in effect, 150 cubic meter per hour, not more. So this is the big problem, the flow resistance on the pipe. And if the flow resistance is much smaller than the pumping speed of the pump, the evacuation time is only defined by the conductance on the pipe, because the effective pumping speed is nearly the conductance. Let me make an example. Here in the room, a lot of people, and they are listening to me, and they are disappointed, and they want to leave the room as fast as possible. Now there's a small door, and only 3 people per second will pass this door, not more. It makes no difference if here are 10, 100, or 1,000 people pressing. Only 3 per second may pass the door. And this will also happen in vacuum technology. There will be a point where the diameter of the pipe is defining the effective pumping speed at the packing machine. We can install more and bigger pumps with no effect. So, very simple. Let's use a big pipe. No problem with the flow resistance, everything clear. But the next point is the effect of the volume of the pipe. If I have a pipe between the vacuum pump and the packing machine, I have an additional volume which has to be evacuated within each cycle. And the volume is depending on the length of the pipe, and it's also depending on the diameter up to 2. So the effect of volume tells us we need small pipes. But the flow resistance, we need big pipes. And that's a problem. I have 2 effects working against. Of course, I can calculate the best fit for the pipe. But nevertheless, the evacuation time becomes much longer than before. Let's make an example. We have a packing machine with a chamber volume of 13 liters. We want to reach a final pressure of 3 millibar. Evacuation time, 1.5 seconds. The pumping speed which is required is 181 cubic meter per hour. I have calculated. So we use a pump 250 cubic meter per hour, normally rotary vane pump. But now the distance between the machine and the vacuum pump is 8 meters. I have calculated first a flexible hose with 1 inch, 43 millimeter inside. The volume of 8 meters of the pipe is 7.3 liters. The conductance is 396. So I need a vacuum pump 800 cubic meter per hour. If I use a 2-inch pipe, more volume, but also a bigger and higher conductance, I only need 480 cubic meter per hour. But if I use a 3-inch pipe with 90 millimeters inside, 51 liter, very high conductance, but now again, I need 680 cubic meter. So for this example, the best fit is the flexible hose in 2-inch. If I have bigger pipe, I have less flow resistance, but more additional volume. So it is possible to calculate the best fit, but nevertheless, instead of 250 cubic meter, now I need 480 cubic meter per hour. And by the way, there are some things which are written in a lot of books about vacuum technology, which are definitely wrong. And one of this is that the diameter of the pipe has always to be the same diameter like the sucking connection of the vacuum pump. And this is pure nonsense. You always have to calculate the best fit. It's not depending on the connection on the vacuum pump. Okay, so evacuation time becomes much longer than before, caused by the additional volume of the pipe and the flow resistance of the pipe. So we will have less cycle performance as before, or we need bigger pump. And now we want to do more than only selling pumps. Because the easiest way is to sell more pumps or to sell a bigger pump. But I would like to have a better solution, better than only selling pumps. So just have to talk a few minutes about vacuum pumps. Mostly used in the packing industry are rotary vane pumps and booster pumps. For the last years, also some screw pumps. But up to now, mostly widely used rotary vane pumps and booster pumps. The rotary vane pump, this is a rotary vane pump, 300 cubic meter per hour. And it's working. We have the inlet. There, the rotor is rotating. We have 3 sleeves which are coming out, caused by the rotation. And at this point, a new volume is opened. The gas particles will go in this new created volume. The volume will be separated and the air is pressed out of the pump. Very easy and well-known function. This is the pumping speed. You can buy a rotary vane pump. You open the catalog and you see, okay, rotary vane pump, pumping speed 300 cubic meter per hour. But this means the pumping speed, the 300 cubic meter per hour, is the pumping speed at atmospheric pressure, at 1000 millibar. During the evacuation process, the pressure goes down, and also the pumping speed goes down and go down to 0. And here, this point is the final pressure of the pump. That is to say, the final pressure of a vacuum pump is the pressure where the pumping speed is 0. So the 300 cubic meter pump we have at atmospheric pressure. At 10 millibar, we have maybe 220 cubic meter hours. At 10 millibar, we have 100 cubic meter per hour. Okay, let's talk about booster pumps. This is a booster pump, also called Woods pump, named by the inventors of the pump, 2 brothers named Woods. They found this pump in the States by removing the counter for gas in their house and adding a motor. We have 2 lobes rotating, and the gas from the inlet is catched and transported through the pump and pressed to the outlet. And that's with a very high rotation. We have up to 3,000 rotations per minute. And the gas is sucked from the upper flange and pressed to the lower flange. This pump is oil-free. We have between the lobes, we have very small space, also between the lobes and the housing, a very small space to avoid that the gas will flow back from the lower connection to the sucking connection. But therefore, we have a big problem. The pump may not become warm. If the pump becomes warm, the volume of the lobes will increase and they will crash. But what do we want to do? We want to evacuate a chamber down to a final pressure of, let's say, 5 millibar. That is to say, we have to take air at 5 millibar and compress to 1,000 millibar. And if we compress the gas, this is defined by the physics, by the first law of thermodynamics. Every compression of a gas will produce heat. No problem to avoid this. It's a physical process. So if we compress the air, we produce heat, and the pump will be destroyed within a few minutes. So therefore, the maximum pressure difference between the sucking connection and the pressure connection is, let's say, approximately 50 millibar. That is to say, the booster pump can only compress from, let's say, 1 millibar to 50 millibar, but not from 1 millibar to 1,000 millibar. So therefore, this pump cannot be used alone. We always need a backing pump. Here's, see the booster pump. We have the sucking connection. We have the outlet. Here is connected a backing pump, which is making the compression work. That is to say, the booster can suck at 1 millibar, compress to 50 millibar, and we need a backing pump compressing from 50 millibar to 1,000 millibar. But now we have to avoid that the pressure difference will be higher than 50 millibar, because otherwise we will destroy the pump. The easiest way to handle this is the so-called overflow valve. It's nothing else than a weight here, and if the pressure difference is higher than 50 millibar, this is pressed up and we open a bypass, and the pump is safe. On the other side, the pumping speed goes down because we have a bypass here around, but we have saved our vacuum pump. So that is to say, we have a backing pump, we have the booster pump, the combination, and the bypass valve. This is the pumping speed of a combination. Rotary vane pump with a booster pump. We start at 1,000 millibar. From 1,000 millibar to, let's say, approximately 100 millibar, the efficiency of the booster pump is 0. The pump is doing nothing, only rotating with opened overflow valve, but no effect on the evacuation process. If the pressure is lower than 100 millibar, the efficiency of the booster pump rises up till we reach the whole pumping speed of the booster pump, and then it goes down to the final pressure. So if you use a booster pump, the effect is only here. But most time, from 1,000 millibar to 100 millibar, the very expensive booster pump is doing nearly nothing. So this is not very satisfying. We have paid a lot of money for a booster pump, but without any effect. So let's make a trick. And the trick is a buffer between the booster pump and the backing pump. And also the buffer, we can use a big pipe, so we can remove the vacuum pump, the rotary vane pump, out of the packing area. Let's remember, we have talked about hygienic problem, warm up in the room, and so on. So therefore, the oil lubricated and hot vacuum pump is out of the room. And here we have the buffer. Now, the vacuum valve opens, 1000 millibar in the sealing chamber. We open the vacuum valve. And now we will have a very, very fast pressure expansion between the small volume of the sealing chamber and the big buffer. The air runs through the booster pump and the pressure drops down directly down to, let's say, 40 millibar. And then at 40 millibar, we have the booster pump directly running with full efficiency and a very short evacuation time. So this is an easy trick to increase the performance of a booster pump, to increase the efficiency. Only in using the big buffer here, pressure expansion down to 40 millibar. And beside this, the rotary vane pump is removed from the packing area. Pre-evacuated buffer, pressure compensation between the sealing chamber and the buffer, and the final pressure, the required final pressure for the packing machine is realized with the booster pump. And beside this, packing pump out of the room, and the evacuation time is shorter than before. So we have removed the pump and we have increased the performance of the packing machine. The booster pump is not a big problem in the hygienic area. We have no oil in the pump. It's a dry running pump. And if it is well calculated, you will see this later on, we will no heat up in the room because the booster pump is only compressing for 50 millibar. And the backing pump make the compression work from 50 millibar to 1000 millibar. Okay, now let's make the same example as before. We have our sealing chamber, 31 liter. We want to reach a little bit lower pressure, now 3 millibar. The machine, we want to have 14 cycles per minute. Evacuation time, 1.5 seconds. We have calculated, okay, we need a pumping speed of 432 cubic meter per hour all over the time directly at the packing machine, at the sealing chamber of the machine. And the distance between the pump and machine, due to the hygienic problems, should be 8 meters. So let's use the booster pump in the machine, 400 cubic meter per hour. And these 400 cubic meter per hour are more than enough. I have seen a lot of packing machines in food processing plants with booster pumps built in the machines. Booster pumps, 1000 cubic meter per hour, 1500, 2000 cubic meter per hour. Believe me, this makes no sense. Not of all. Let's make a short calculation at this point. We have the sealing chamber, the packing machine. Then we have a lot of valves in the packing machines. In the packing machine, there are valves for upper vacuum, for lower vacuum, for product vacuum. They are connected together. And then out of the machine, we have the sucking, the connection for the vacuum pump in 2-inch. Now we install a big pump here, a booster pump. We have the effective pumping speed at the chamber. We have the flow resistance the internal flow assistance in the packing machine, and we have the installed vacuum pump. As you have seen before, the effective pumping speed is 1 over the pumping speed of the pump plus 1 over the conductance. If we have, let's make an example. We use a vacuum pump 500 cubic meter per hour. The conductance in the packing machine is also 500 cubic meter per hour. So the effective pumping speed is 250 cubic meter per hour, not more. And now we use a bigger pump, 2000 cubic meter per hour. Now I need my calculator. The effective pumping speed as effective is now 400 cubic meter per hour. That has to say, we have installed a pump 4 times more pumping speed than before, but we have only 150 cubic meter more. So the problem is, it makes no sense to use such big booster pumps in packing machines because of the conductance in the machine. Much better is if we have the booster pump running all over the time with full efficiency. What you have seen before makes much more sense than installing bigger and bigger booster pumps. Okay, so makes no sense to have a big booster pump. Let's make a clever solution. Booster pump in the machine, buffer volume, and backing pump outside. Yes, please.
So I have a question. Okay, these calculations depends on the vacuum, the final vacuum, or it's always the same calculation? It's works with okay, say packaging, or it's the same with another applications?
It is always the same. This equation is not depending on the pressure, not at all. This is over the whole range of the pressure, but the conductance is depending on the pressure. So the conductance on a pipe changes from 1000 millibar to 1 millibar, and there's an extremely change in the pressure. This is the reason why it's a little bit complicated to calculate the conductance. But nevertheless, this equation is not depending on the pressure. It's for the whole range. Okay, we have our packing machine. We have learned a booster pump 500 cubic meter per hour is more than enough. We have the buffer and the backing pump 250 cubic meter per hour. What will happen? Sealing chamber, booster pump, volume. Let's have a look to the pressure over the time in the volume here. The backing pump is running. The buffer is evacuated. We have 1 millibar. Now, the vacuum valve opens, pressure expansion. The pressure rises up. Final pressure is realized by the booster pump. Vacuum valve is closed, so the pressure goes in the buffer goes down with the E function. Next cycle, pressure goes up and goes down. And afterwards, the pressure is always going up and down. We start 1 millibar in the chamber and 1,000 1 millibar in the buffer volume and 1,000 millibar in the sealing chamber. Vacuum valves opened, the pressure rises up to 22.2 millibar. Vacuum valve closed, and the pressure goes down to 30.5 millibar. Please remember, we have the full efficiency of the booster pump if the pressure is lower than, let's say, 45 millibar. So it's no problem to reach 1 millibar final pressure in the pump, in the sealing chamber. Next cycle, pressure goes down 34.4 millibar. Vacuum valve closed, pressure goes down 20.9. Final pressure 1.1. Pressure goes up and down, up and down. And now we see the pressure, the maximum pressure rise up. And now we can't reach the desired final pressure in the sealing chamber. So this will not work. After 6 or 7 cycles, they stop the machine because the machine shows on the display not enough vacuum. They stop the machine. The backing pump is pumping down the buffer to 1 millibar. They have a look to the machine, start again. It works, 6 cycles, stop again. Okay, so there's something wrong with the buffer or with the pump. Okay, let's try. Let's use smaller buffer and a bigger pump. Just try it. Same again, but now after 3 cycles, the pressure in the buffer is too high. This does not work too. Okay, try the next thing. Bigger buffer again, but maybe smaller pump. And now it works. So this is the problem with such a system. This system has to be calculated very well, because otherwise it will not work. So for each packing machine, depending on the volume in the sealing chamber, and depending on the required performance of the machine, I have to calculate the system. And I've seen a lot of systems which are not working. And if I go to a packing machine, sometimes I can hear it. Because if I stand beside a packing machine with a built-in booster pump, and I hear the booster pump is making a noise like a tram, going, ooh, ooh. Then I know, during this time, when the pump is so loud, the efficiency of the pump is 0. So therefore, this system has to be recalculated. So the so-called combined, yes, please.
Okay, so another question, sorry.
Please.
And what's the way? Who can I know what buffer I need and what pump I need and so on?
This has to be calculated.
Ask you. Yeah.
Yes, you have to ask me.
Perfect, thank you
Yeah.
very much. So I'm going to do.
It's not so easy. This calculation is not so easy. I can give you one equation, you can put in all values and we will have the result. This is not possible. Okay, the so-called combined system, it's also possible to make this for more than one machine. I have one backing pipe, a big pipe, backing volume. I have the central vacuum supply out of the hygienic area. And in the machines, booster pumps are built in. And that's a problem. For each packing machine, a booster pump is required. And therefore, this system is useful for packing plants with 2 or 3 packing machines. If there are more packing machines, this is much too expensive. I have seen a lot of vacuum supplies, the so-called combined systems. I have seen one approximately 8-10 years ago in Scandinavia, in Norway, a big meat processing plant with 20 packing lines. In each packing line, a booster pump, 2,000 cubic meter per hour. And in the machinery room, 6 rotary vane pumps, each 1,000 cubic meter per hour. And this is absolute nonsense. So we have 20 packing lines, each with a booster, 2,000 cubic meter per hour. Then rotary vane pumps, 1,000, each 1,000 cubic meter per hour. First thing, we have seen before, if the system is well calculated, it makes no sense to have a 2,000 booster here. 500 is enough. The next point is rotary vane pump with 1,000 cubic meter per hour makes no sense in such a system. Let's make an example. I have a rotary vane pump, pumping speed 300 cubic meter per hour. 5.5 kilowatt. That means 1.83 kilowatt per 100 cubic meter per hour pumping speed. 500 cubic meter per hour pump. We have 11 kilowatt. That means 2.2 kilowatt per 100 cubic meter per hour. 1,000 cubic meter per hour with minimum 20 kilowatt, minimum. Most times they have 30 kilowatt. That means 2.0 kilowatt. This is point 1, not to use such big rotary vane pumps. Point 2, the cost for lubricants, for oil, for filters, and so on. They are rising up. So this makes no sense. This makes no sense. And the whole system makes no sense with 20 booster pumps in each packing machine. Oh, sorry. There's one good reason for this system. One good reason: to sell pumps, to sell big pumps. But that's all. So that is to say, for a food processing plant with, let's say, more than 4 packing machines, the combined system makes no sense. It is sometimes used because it is easy to calculate and easy to build up such a system. But if we have more packing machines, we need another solution. And the best solution here is the totally centralized vacuum system. That is to say, no more vacuum pump in the packing room. We have 3 packing machines, and now we have 2 vacuum systems. One is called rough vacuum, one is called fine vacuum.
Sorry.
Please.
I have a question.
Yes, please.
Are you talking to us that, are you explaining that we can take out the the roots from the clean areas, from the clean rooms?
Yes, exactly. This is what I want to show you
Really?
now.
But all the time, someone tell us that that is impossible, that the roots have to stay so close with the machines and so on. This is not truth.
It is true if you make the combined system with a booster at each machine and one buffer pipe.
Okay.
Then we need the booster. And then you're absolutely right. The booster has to be directly as near as possible to the sealing chamber at the machine.
Okay.
But this is only if you have the combined system with one pipe. But now I want to show you a better solution.
Okay.
Without any pump in the packing room.
Wow. Sounds good. Thank you very much.
You're welcome. So we have no booster in the machine, but now we have two pipes. One called rough vacuum, one called fine vacuum. In a machinery room, you have the vacuum pumps. The rough vacuum will be evacuated to a pressure level of approximately, let's say, 50 millibar. And the fine vacuum is evacuated to a pressure level of 2 millibar. Each packing machine is equipped with a special valve block. There are two valves beside, connected to the sealing chamber. One valve is connected to rough vacuum, the other valve is connected to fine vacuum. Now, if the machine wants to evacuate 1000 millibar, we open the valve to the rough vacuum. And we have a very fast pressure expansion between the chamber and the rough vacuum. The pressure goes down from 1000 millibar in the sealing chamber to 50 millibar rough vacuum level. We close the valve, short delay, and we open the second valve and a second pressure expansion down to 2 millibar. And this is the fastest possible evacuation of a fixed volume. The evacuation by pressure expansion. And this is the so-called double-stage pressure expansion. The evacuation time we need now is only depending on the internal flow assistance in the packing machine. Because with the pre-evacuated buffer, we have nearly a non-ending pumping speed installed in front of the machine. So this is the fastest possible evacuation. But now the question is, why do we need two stages? Why do we not only use fine vacuum? We save one pipe, only fine vacuum, 2 millibar, faster than before. And therefore, I have a small example, but I think we just talk about the vacuum system, the central vacuum supply, with two pipes, two systems called rough and fine vacuum. And the question is, why do we need two pipes, two systems? So let's make an easy example. We have at the University of Cologne a physical lab. In the lab, we have a pipe. And downstairs, we have a big unit for compressed air, a big compressor. And in the lab, we have the pipe with connections for each working place. Now it's a physical lab. They are starting with an experiment. The first student arrives early in the morning, 10:30. He is connecting his equipment. He is opening the valve, and he has compressed air. Pressure is coming out. The next guy arriving half an hour later, connecting his equipment, open the valve, and also he receives compressed air. Air is coming out. It's less air than this one had before, because now there are two machines connected, but nevertheless, air is coming out. 1 week later, the same physical lab, but now we have a system with vacuum. Big central vacuum supply downstairs, and in the lab, ball valves for each working place. First arrives early in the morning, 10:30, connecting his equipment, opening the valve, and the air is going out. He says, okay, everything is work. He goes downstairs to have a coffee. The next one arrives half an hour later, open the valve, the air goes out and back at the first working place in. And this is the big difference between vacuum and compressed air. If you have a compressed air system, you open a connection, air will always come out. It will never happen that air is going in. But the change in flow direction, this is possible with vacuum. And now, if we have one vacuum pipe, one central vacuum station, and 5 packing machines, the first machine want to reach, let's say, final pressure 5 millibar. At 10 millibar, the next machine opened the valve. Then we have to avoid that the pressure here rise up again from 10. So therefore, we need an enormous volume and an enormous pumping speed here. And this makes no sense. It is possible with one pipe, but only if we have booster pumps in. But without booster pumps, with one pipe, will not work. And the trick is the 2-stage. The first machine, rough vacuum, close, open, fine vacuum. Let's say we are here at 20 millibar. The second machine opens, but the first pressure expansion go to the rough vacuum, not to the fine vacuum. So therefore, the treatment between the machines is not from 1000 to 3 millibar, it is only from 50 to 3 millibar. And this was the trick patented by my father in 1979 to use a double stage pressure expansion. So we have the fastest possible evacuation of the vacuum chamber by a double stage pressure compensation between rough and fine vacuum. First 50 millibar rough vacuum, short time delay, 2 millibar fine vacuum. The shortest possible evacuation time, the time now is only depending on the internal flow resistance in the packing machine. And we have no vacuum pump in the room. So the advantages, shorter evacuation time, and we have less power demand. First of all, we do not have the vacuum pump in the room, the heat up of the room. So we are saving energy for the cooling of the room. And the next point is we need less vacuum pumps than before. But why this? Normally, this can't be. We have removed the vacuum pumps from the room. The machines becomes faster than before, and we need less pumps. Why? So, what is the vacuum pump doing? If the vacuum pump is in the packing machine, built in the packing machine, running at final pressure, doing nothing, and then once a time for the evacuation, evacuate. Stand, evacuate, and so on. That is to say, the machine is running with 10 cycles. That means 10 times a minute, the vacuum pump is running for 2 or 3 seconds, have a big load, and afterward, the rest of the time, standing there and doing nothing. And the vacuum pump in a central vacuum station is running at a constant level all over the time at 50 millibar. That is to say, we have integrated the load on the vacuum pump over the time. It's nearly the same if I go with my car, I drive from, let's say, Cologne to Frankfurt, 200 kilometers. I do this by starting acceleration, my car, from 0 to 210 kilometers per hour, stop, wait a minute, and once again. When I arrive in Frankfurt, I will use a lot of gasoline and I will damage my car. Or otherwise, I go on the highway and I drive at a mean level of, let's say, 120 kilometers from Cologne to Frankfurt. And nearly the same with the central vacuum supply. We have a better use of the vacuum pump over the time. And we have less load on the pump. Next point, in a central vacuum supply, we will always have a standby pump. Because this is a problem. If you know, let's say you have 10 packing lines with built-in vacuum pumps. If a vacuum pump fails, you have to stop one line. Okay. But in central vacuum supply, if the pump fails, there is a standby pump which is integrated in the system and which is fully automatically turned on. That is to say, if a pump fails, you have not 1 second without production. If you have time, go to central station, check what has happened, and repair the pump. The same is today, if you need to make maintenance work at the vacuum pump, you have to stop the machine, or you have to do it in the late evening hours or on weekend. In central vacuum supply, no problem. Turn off the vacuum pump, the standby pump turns on fully automatically, and you can do the maintenance work during the normal working hours. And most of all, the hygienic aspect. You have no more danger of oil contamination in your production. So the working principle, we have the packing machines.
So, sorry, Felix, could I have a question?
Yes, please. Yes, please.
Yeah. Could you please explain these signs? What kind of pumps are these that you draw here?
Yeah.
Yeah. Because could you explain more or less what is the
very good question.
Thank you very much.
Yeah. Now, before I have talked about two vacuum systems called rough and fine vacuum. Rough vacuum 50 millibar, fine vacuum at 2 millibar. Now we have a third system here, auxiliary vacuum. The auxiliary vacuum, this vacuum is used for the forming of foil. Why this? It's also possible to connect the forming station to the rough vacuum. Yes, of course, it's possible, but it's not clever. Because we have seen before, for the forming of foil, we need, let's say, 150 millibar. It's more than enough. Only, also, if you have a very thick film, maybe sometimes you need 180 millibar. More than enough. Normally, let's say 150 millibar. More than enough to form the foil. If we connect rough vacuum, we have to evacuate down to 50 millibar within each cycle. And that makes no sense. And what do we want? We want to save energy, we want to save costs. We want to minimize the number of pumps and the size of pumps. So therefore, a much better, a much clever solution is to use a third pipe. The system is called auxiliary vacuum. The pressure level is between 100 and 150 millibar. And there we connect the forming station. Okay, what kind of pumps do we have? For the auxiliary vacuum, normally used rotary vane pumps. Also possible screw pumps. Sometimes it is very good to use screw pumps because maybe, let's say, if you have a very thin film, let's say 200 or 250 millibar is enough for the forming of foil. But if we run a rotary vane pump at 200 millibar, there is a big load on the pump. The pump becomes very hot, and the pump do not like to run at such a high pressure. And then it's better to use screw pumps. Try running screw pumps without any oil. They are nearly maintenance, or much less maintenance than for a rotary vane pump. So for this case, screw pumps are the best solution. I think they're a little bit more expensive than rotary pumps, but calculate the cost and the cost for maintenance and lifetime. So therefore, for auxiliary vacuum, rotary vane pumps or screw pumps, the best pumps. For rough vacuum, at rough vacuum, we need a pressure level of 50 millibar. So yes, please.
Sorry. See? Okay. What happens if we have hot product in the, what we want to seal is hot product, and what the humidity? Ah, yes. Right.
Sorry. Good.
What happens with the hot products? If we have a hot product in that we want to seal, the humidity of it?
Yes,
and
that's
the water?
a very good question. If you have hot products like bread, fresh bread, warm bread, or you are packing soups or anything else, then you will not go down to a pressure, let's say, lower than 50 millibar. You can't reach a lower pressure because use a vapor pressure of the product. So then the centralized vacuum system will be adapted on the product, and then we only have, maybe we have only one pipe for final pressure of 100 millibar. Or sometimes two pipes, we have 150 millibar for the final pressure. So the system is always especially designed for the customer, especially designed for the machines, for the kind of machines, and for the products. And I think I have calculated nearly 1,000 centralized vacuum systems. I have never had two which are exactly the same. And all the central vacuum suppliers we have built up to now, each system is a special design system for the customer. Okay, so go back to the rough vacuum. We need 50 millibar. 50 millibar, we may use a rotary vane pump, we may use a screw pump. But I would prefer to use a combination of a rotary vane pump and a booster pump due to the power consumption. I may use, let's make an example. Rough vacuum system, I need 50 millibar. I have calculated my system and I've seen, okay, I need pumping speed 500 cubic meter, let's say 1,000 cubic meter per hour. Okay, 1,000 cubic meter per hour, I can realize with two backing pumps, each 500 cubic meter per hour. That means 22 kilowatt. Or I use one booster pump, 1,000 cubic meter per hour, and two backing pumps, 300 cubic meter per hour, 5.5 kilowatt, 3 kilowatt. That means 14 kilowatt. And that's the reason why I like to use booster pumps. Booster pumps, they have a very high pumping speed with a very low power demand. And in the centralized vacuum system, I can install and run the booster pump always at the point of best efficiency. So therefore, we need booster pumps because we want to save energy. That is to say, for the rough vacuum, we have a combination of booster pump and backing pump, rotary vane pump, or also possible a screw pump. Fine vacuum. For fine vacuum, I also, for the same reason, I need a booster pump. But now, I do not use a backing pump. I have a second booster pump and then go back to the WAF vacuum. Why this? We have WAF vacuum, 50 millibar. Fine vacuum, 2 millibar. I have a booster and a backing pump, 1,500 means 14 kilowatt. But I can save this pump. I do not need this pump if I compress directly to the WAF vacuum. I have an additional load on the WAF vacuum because the air of the fine vacuum also goes into WAF vacuum. But this is not a lot because the volume of the chamber from 1,000 millibar to 50 millibar goes to WAF vacuum. So that's to say most of the air, 950 millibars multiplied with the volume, goes to WAF vacuum. And only a small amount of the air from 50 millibar to 2 millibar goes to fine vacuum. So for WAF vacuum, it makes no big difference to add also the air from the fine vacuum into the WAF vacuum. And I do not need a 500 cubic meter pump, and I can save 11 kilowatt. So therefore, the fine vacuum is evacuated by a booster pump, which is compressing to the WAF vacuum. But why do we have two pumps?
Hello, I have a question in the chat from David to Bern and say like one question, when does it make sense to apply this hybrid fine and route vacuum system between which pressures, if from where to where? I don't know if it's so clear. Is this always the best solution? So when makes sense to put the two rings or?
Yeah, it is depending on the number of packing machines, and it's depending of the performance and the required final pressure of the packing machines. Normally, you can say 1 or 2 packing machines. Best solution, combined system. More than 5 machines, no doubt you need a centralized system with 2 pressure levels. If you have 3 or 4 machines, sometimes I will calculate both versions, just to have an idea which is the better one. So if a customer has 3 machines, most times I calculate a combined system and I calculate the centralized system. And I tell the customer, okay, you have combined system, costs approximately this and this, or the other system costs like this and this. Now it's up to you to decide. And it's also a question, if the customer has a big plant and he knows exactly, okay, I want to grow up my production over the next 5-10 years. I have enough space in my packing room, and I think the next years I will add more machines. Then it's also possible for 2 machines to start with a centralized system with 2 pipes. So it's always depending on the customer. Okay, yes, please.
How much space does this system occupy? Do you need a lot of space room?
Maybe later on I will show some pictures of central vacuum system, because this is also depending on the customer, how many machines. So we have built centralized vacuum systems. You need a space, let's say 2 meters at 3 meters. And we have a system built where we need the whole room like here, like we have here. Okay, I just want to come back to the fine vacuum. I have now explained that we use a booster pump and that we connect to WAF vacuum for saving energy. But here I have 2 booster pumps. Why do I use 2 booster pumps? The effective pumping speed of the system is given by the bigger pump on top. So it's no question of pumping speed. The problem is the pressure difference. If you remember, we have talked about the booster pump, maximum pressure difference, 50 millibar. If I have 50 millibar at rough vacuum and I want to reach 1 millibar at fine vacuum, the efficiency of the booster is very low. So therefore, I need 2 booster pumps, and now I can run a higher pressure difference between the rough and the fine vacuum. So the second pump is only to realize the pressure difference between rough and fine vacuum. And this pump has to be smaller than the upper pump, so that I can divide the pressure difference to the 2 pumps. That's the reason why I need 2 booster pumps here. We have the rotary vane pump for auxiliary vacuum. We have a combination rotary vane pump and booster pump for the rough vacuum, and the 2 booster pumps for the fine vacuum. At the packing machine, the forming station is connected to the auxiliary vacuum. In the machine is integrated a vacuum valve. It's needed in the machine. So we do not need any more valve or anything else. We just connect with a flexible hose to the auxiliary vacuum, finished. For the sealing chamber, we need to add a valve block for the rough and the fine vacuum. And this valve block is connected to the sealing chamber as near as possible. And then we can connect to rough and fine vacuum. Let's make an example. In this example, the auxiliary vacuum for the forming station of foil is in a pressure level between 50 and 300 millibar. Yes, please.
Another question. For this auxiliary vacuum, if we have machines, different machines with these needs of 150 millibar more or less, I think it happened the same. If I connect one and connect the other, the vacuum, the pressure come back from one side to the other, no?
Yes, but now we are at a pressure level between 50 and 300 millibar.
Okay.
So it's only a treatment from one machine to another, from 1,000 to, let's say, to 200 millibar.
Yeah.
It is the same what I have in rough vacuum. I can handle this. The problem is if I need to go lower than 10 millibar, then with one system becomes too expensive. Okay, the auxiliary vacuum for the forming of foil. This, we have sometimes, we have installations only with 2 pipes, only with rough and fine vacuum. This is depending on the packing machines. If the customer has thermoformers which do not need vacuum for the forming of foil, then we do not need the auxiliary vacuum. It is also possible to form the foil with compressed air or with a stamp. So sometimes, if the customer needs no vacuum for forming of foil, we only have rough and fine vacuum. If we need vacuum for forming of foil, then we need auxiliary vacuum. And there's another point. Sometimes the customer tells me, oh, I have a big chamber machine, like a VC999 or SuperVac, Webomatic, big chamber machine, a volume 1, 2, 300 liters. And everybody tells me it's not possible to connect these big machines to a centralized vacuum system. That's wrong. But you need a trick. We have the rough vacuum, 50 millibar. We have the fine vacuum, 2 millibar. And we have a packing machine connected to rough vacuum and to fine vacuum. The pressure in rough vacuum goes up If the valve opens and then go down, you go up and down over the time. Now, this is a packing machine, let's say the volume of 20 liters. Now, I connect a big chamber machine with 200 liters. Connect to our vacuum and connect to fine vacuum. And now, when this machine opens, the pressure rises up very high due to the big volume, to the 200 liters. Or there are big trimmer machines with 400 liters volume. So therefore, it's not possible to connect these big chambers to centralized vacuum system. It is, if we use a trick. And the trick is, you have the third system called auxiliary vacuum at 100 millibar. And here, for these big chamber machines, we make a three-stage pressure expansion. First step to auxiliary vacuum, the pressure goes down from 1000 to 100 millibar, and then connect to VAF vacuum. And then it's exactly the same load for the VAF vacuum as if we have a smaller thermoformer with 1000 millibar. So that is to say, if we need vacuum for the forming of foil for a thermoformer, or if we have big chamber machines, then we need three systems. If you have no chamber machines, no vacuum for forming is required, then also a system with two pipes, only VAF and fine vacuum is possible. So the auxiliary vacuum only used in three-level installation, used for the thermoforming process. It's used for the big chamber machines. And we use oil lubricated pumps, rotary vane pumps, or dry running screw pumps. The pressure in auxiliary vacuum is depending on the type of foil. If I have a thin foil or a thick foil, what kind of foil. It's depending on the depth of draw, on the size. It is depending on the type of the heating. We will talk about this later on. And we have the VAF vacuum. The VAF vacuum can be between 20 and 100 millibar. It's up to me. Because I always tell my customers, when I calculate a centralized system, I play. It's a game for me. Because I have a number of machines. I have information about the machines. I have existing pumps. And then I calculate. Okay, one pump here, one pump there. I calculate pressure level of VAF vacuum, 50 millibar or maybe 80 millibar. If I have 80 millibar in VAF vacuum, more gas will go to the fine vacuum. And so it's a game. And I play, and then I say, okay, this is the best version to have the effect with the with lowest number of vacuum pumps, to use less pumps and to reduce the power consumption. So therefore, this is up to me what pressure in the VAF vacuum you will have later on. The VAF vacuum is always used in 2- and 3-level installation. It is for the thermoformers. For the first step to VAF vacuum from a thermoformer, or if you have a chamber machine, the second step from auxiliary to VAF vacuum. You always lose oil lubricated rotary vane pumps, dry running screw pumps, and booster pumps.
Sorry, could I have a question?
Yes, please.
What is the importance of raw vacuum in productivity? When you calculate how many raw vacuum do you need, or how many millibars, or the size of the pipe, do you take in account productivity?
Yes, of course, because the required pumping speed in VAF vacuum and in fine vacuum is depending on the number of machines, And it's depending on the product of the volume of a machine multiplied with the performance of the machine. So I need to know the volume of the machine. I need to know the desired performance of the machine. And the product of the volume and the performance, this make the gas load for the system. And therefore, for the total number of packing machines, I have my gas flow, the gas flow which is coming to the rough vacuum. And then I can calculate the required pumping speed to reach the desired pressure. And as I've explained before, the pressure, this is up to me.
Yes. Hello, one question from my side.
Yes, please.
Do you need the volume of the machine, the volume of the chamber, or the volume that should be extracted out of the chamber? I mean, with product inside the chamber. Yes. For your calculation.
Yeah.
And what difference make this?
Yes, it is a big difference. It is a big difference. The first difficulties we will have for the forming station, for the heating, we will see later on. And the next is to calculate the volume from the ceiling chamber is not so easy. It is depending on the size of the chamber, but it's also depending on the product. And it's depending on, let's say, the filling of the package. Because you can form a mold, let's say 100 millimeters, you have a big package, and you pack only a small piece of meat inside. It makes not a big sense. I can show you later on why, because there's another big problem. But then you have a lot of air around the product, which has to be evacuated. Or you have a package which is fulfilled, 80% of the package is filled with product. So I have less volume to evacuate. So therefore, to calculate the required pumping speed, you have to calculate the volume of the machine, and therefore you need a little bit experience.
Thank you very much. I have another question in the chat, coming from Mr. Heckers Bruchhaus, from Germany. So could we use or dry running rotary vane pumps for the auxiliary vacuum? Oh, sorry, could we use glow or dry running rotary vane pumps for the auxiliary vacuum?
Yes, yes, of course. It's also possible, as I've explained before, the problem in auxiliary vacuum is with the oil lubricated pumps because they have enormous load at the high pressure. It's also possible to use dry running rotary vane pumps. But the problem is most dry rotary, I know dry running rotary vane pumps with a pumping speed, let's say maybe up to 100 cubic meter per hour, not more. Point one. Point two, you have to check the final pressure of the dry running rotary vane pumps, because sometimes they have only a final pressure of 50 millibar. Should be no problem, because we need 100. There is a problem. And very often, customers are not aware of this problem. Now, this is a good chance to talk about this. As I've explained before, the pumping speed of a rotary vane pump is depending on the pressure. The curve is like this. So let's say we have a rotary vane pump with a pumping speed of 300 cubic meter per hour at atmospheric pressure. The final pressure is 1 millibar. Okay, so it's no problem to use this pump at 2 millibar, at 3 millibar. It is possible, but then I do not have 300 cubic meter, I have only 50 cubic meter per hour. So that is to say, the final pressure of a vacuum pump has to be much lower than the desired working pressure, because we want to be in this area with the full efficiency. So therefore, sometimes it's difficult with dry running rotary vane pumps. But nevertheless, it is possible to use them, mostly for auxiliary vacuum, because they may run at a higher pressure level. This is absolutely right. Okay, back to the WAF vacuum. The pressure is depending on the pumping speed on the sealing chamber and on my idea from the centralized system. We have fine vacuum. The fine vacuum is always used in 2 or 3 level installations if we need a low pressure. If the customer is packing bread or anything else at 100 millibar, no fine vacuum is required. But for all meat processing plants, I think you need final pressure lower than 10 millibar, then we need a fine vacuum system. It is used for the sealing chamber, for the evacuation, is generated, or we use only booster pumps due to the power consumption. And the pressure is depending on the desired final pressure. And also very important, we have a packing machine, and the desired final pressure, depending on the product, let's say is 5 millibar. Okay, so I make a centralized vacuum system, WAF vacuum with 50 millibar, and fine vacuum with 5 millibar. Because the desired final pressure for the machine is also 5 millibar. I think you won't be happy with this system. The pressure in the fine vacuum system has to be lower than the desired final pressure, because otherwise we won't reach the speed of the packing machine. We want to evacuate with a double stage pressure expansion. WAF vacuum, short time delay, and down to fine vacuum. But if we have 5 millibar here and 5 millibar here, the very near pressure, so I will have no gas flow. The gas flow needs too much time, so evacuation curve will be like this. So therefore, the pressure level in fine vacuum has to be lower than the desired final pressure in your packing machine. And beside this, you also need a little bit more pumping speed to avoid any problem if you have a small leakage in the package machine. And you will have leakages at packing machines. Minimum 3 millibar. Okay. So the question was, what pressure difference is needed between the fine vacuum and the desired final pressure in the packing machine to avoid the problem with the gas flow? So minimum, let me say, is 3 millibar. Better is 5 millibar. So there, it's a good chance to talk about high vacuum lines or skin machines. A lot of products are packed with a skin package. The foil is pressed like a skin on the product. And today it becomes more and more common to use flat skin machines. And for skin or flat skin machines, require the final pressure in the sealing chamber should be less than 3 millibar, let's say 2 millibar. Otherwise, you will not have a good package. It will not look very good. And that's a problem for a centralized vacuum system. Because if I have fine vacuum, I have one machine. I have auxiliary vacuum, that's clear, but only have a look to the fine vacuum. This machine needs a final pressure of 10 millibar. The next machine, final pressure, depending on the product, 8 millibar. And there's one flat skin machine with 2 millibar. So that is to say, for these two machines, the final pressure in fine vacuum should be, let's say, 4 millibar. More than enough. But for the skin machine, I need 1 millibar. normally lower than 1 millibar. That's not possible in centralized system. So I have to drop down the pressure in fine vacuum from 4 to 1 millibar. That means I need 4 times of the pumping speed in fine vacuum. Only for this machine. Maybe for these 2 machines, I have a booster pump 1,000 cubic meter in fine vacuum. If I connect this machine, I need 4,000 cubic meter. And this makes no sense. That is to say, if the customer has a skin machine, a flat skin machine, or a high vacuum line, then we have to add a booster pump here, a small booster pump here. Only for this machine. It's not the same like the combined system, what you have before, but we also have rough vacuum. Also rough vacuums connect to all machines. But for the high vacuum line, for the flat skin machine, we need an additional small booster pump. And this is much cheaper, a small 500 cubic meter pump, than adding much more pumps in the fine vacuum. So therefore, this was a very good question. And then, once again, we don't want to sell a lot of pumps, and we don't want to sell big pumps. We want to sell the best solution, the clever solution. And the clever solution in this way is to add a small booster here. So we have talked about this, that the pressure on the fine vacuum has to be much lower than the desired final pressure of the packing machine. Let's have a look again on the evacuation curve. With the integrated vacuum pump, with the vacuum pump in the packing machine, the pressure goes down following the so-called E function. And with the 2-level central system, we go down to 50 millibar, short delay, and then very fast pressure expansion down to 2 millibar. It's just to show that with the centralized vacuum system, we will save time. Faster evacuation. That's it. If you need a final pressure, let's say here, 10 millibar, this is the time you save. Your machine becomes faster with the centralized system. And this is with the integrated vacuum pump. The time, here we have the pressure in a logarithmic scale. Then we have in a logarithmic scale, we have this curve for the integrated pump and the 2-level central system. Here you can see again the difference, the time saving. Here we need to reach the final pressure. Here we need 0.44 seconds, or here 0.12 seconds. And that's the difference. And that's what we want to have. Very fast evacuation. Beside this, there's a second good reason to have a fast evacuation. Maybe we are at a good point to talk about water, about vapor. Because a lot of products, they are wet. Most of all, meat products, they are wet. Let's say we have water. And water is the biggest enemy for each vacuum engineer. Because what will happen? If we have a vacuum chamber, and in the chamber we have water. We connect a vacuum pump here. We evacuate till we reach the vapor pressure of water. What does it mean, the vapor pressure of water? If I have water here, there are always some particles which are leaving the liquid. And also some parts are falling down again. So there's always a lot of parts going from the liquid state to the gas state and from the gas state to the liquid state. And the number of particles here, the number of water particles in a gas state, they're producing a pressure, the so-called vapor pressure of water. And the pressure of the water particles is depending on the number of particles multiplied with the constant and multiplied with the temperature. And that I can make a curve, the so-called vapor pressure curve of water. The curve looks like this. This is the vapor pressure of water depending on the temperature. And there's one point which is very well known. It's the boiling point of water. Because if the temperature is so high that all the particles want to go into the gas state, they will leave, suddenly they will leave the surface, and this is what we are calling boiling. And this point is at 100 degrees, the vapor pressure is 1000 millibar. So the pressure is so high that all the particles can leave the water surface suddenly. This is called boiling. And if you go on a high mountain where the atmospheric pressure is lower, the water boils earlier. That's a well-known effect. So let's go back to the evacuation. Let's say the temperature is 20 degrees and we do not have water, we have fresh meat, wet fresh meat in the package. Temperature of the meat, 20 degrees. At 20 degrees, we are, let's say, here, and the vapor pressure, it's, I don't know, 8 millibar. I'm not sure, but in this range. Now we go down, the pressure goes down, and at the point of 8 millibar, the vapor, the water of the product comes up. So the pressure will not go down because we are only boiling water from the product. So the final pressure is 8 millibar. No, we can go deeper because of the cooling effect. You know this, if you take a shower, early in the morning, take a shower, go out, open the window, you feel cold. Why? Because the water on your body, on the surface of your body, due to the wind from the window, has to be boiled, and therefore energy is required. And this energy is drawn from your body. And the same happens here. We are drying the product, therefore we are cooling down the product, and though we are going down on this curve till we reach the desired final pressure. But now we need time for getting water out. We are losing weight of the product, and we don't like this. So it makes no sense. So therefore, the first thing is, in general, you have to pack your product as cold as possible. If you have a cold product, it has to be packed as cold as possible. Otherwise, you will have a problem. And the next point is, with the centralized vacuum system, I'm evacuating very fast. And what happens if you have a fast pressure expansion? Have anybody opened a bottle of champagne? What happens? What happens if you open a bottle of champagne? What will you see? Fog. Fog. You open a bottle of champagne and you see fog in the bottle. And this is due to the fast expansion, because a fast expansion makes a very short cooling down. In physics, it's called an adiabative expansion. And that means cooling down, and therefore you have the fog. It is condensated water, what you see, only for a short second. And the same happens if I evacuate very fast. I have a fast cooling down, and I may reach a lower pressure than with a normal single pump in the machine. So therefore, these are two different physical aspects. One is the cooling caused by the vaporization of water, and the other one is caused by the expansion. We may not mix this.
Okay, sorry. I have another question from the chat from David Tubern. Another question: to calculate the volume of the fine vacuum collector, can we add the total volume we need for the total machines working at the same time, or it can be lower as long as we keep the vacuum pressure lower than required pressure?
Yes, I think I've got the question. It's a very good question. Once again, only fine vacuum. So we have number of machines connected to fine vacuum. The pressure in fine vacuum over the time is always going up and down. Always up and down. The mean value of the pressure, PM, is only depending on the installed pumping speed in the central vacuum system for a given number of machines. So if I add more pumps, I can press the whole curve down. So this is the mean value, only depending on the pumping speed. But the pressure difference between lowest and highest pressure, this is only depending on the volume of the pipe here. So this is the next step where I make my game in calculating the central vacuum system. I can add more pumping speed to press the curve down, or I can increase the volume to press minimum and maximum together. Everything is possible. I always have to be lower than a given maximum level. At this point, I will calculate the maximum pressure in the fine vacuum. I will calculate at the time if all packaging machines are evacuating exactly the same time. Finished. No discussion about this. You can argue if I have 10 packing machines, it will never happen that 10 machines are evacuating at the same time. Yeah, okay, from the statistic viewpoint, you're absolutely right, but it may happen. And therefore, I calculate always the volume and the capacity of a central vacuum system that all machines are evacuating exactly at the same time, without any discussion. So here it's shown again. We want to reach a final pressure of 5 millibar. We can have this with the integrated vacuum pump within a time of 0.3777 seconds, or double stage pressure expansion, first down to rough vacuum to 50 millibar, and then second pressure expansion down to the required final pressure of 5 millibar, or sorry, 3 millibar. Okay, how can we connect a packing machine to a centralized vacuum system? We have talked about this before. We need rough and fine vacuum. Normally, we have one vacuum connection at the machine where the vacuum pump is connected now. And this can the modification of the packing machine may be done by the manufacturer of the machine. Most of all, if the customer buys a new machine, all well-known producers of packing machines, they all offer packaging machines directly designed and prepared for connection to central vacuum supply. That is to say, the machine is equipped with valves for rough and fine vacuum and can directly be connected to the central vacuum system. Existing machines can be modified by the manufacturer of the machine, or if desired, we can do this, the modification. For this, we have a modification kit. We have the valve block, 2 valves, rough and fine vacuum. They will be connected to the sealing chamber. We install a pressure transmitter in the machine to measure the pressure in the sealing chamber. And we install a very small electrical unit. So we do not treat the machine in any way. We only need power supply and compressed air. We check the pressure in the sealing chamber. If the pressure is between 1000 millibar and 50 millibar, we open the rough vacuum valve. If our transmitter says, okay, we are lower than 50 millibar, we close rough vacuum valve and open fine vacuum valve. The packing machine will not realize that there is no more vacuum pump in, because we have no effect on the machine. But nevertheless, it's also possible that this modification is done from the manufacturer of the machine. From the technical viewpoint, it is a clever solution, a nicer solution, because they have a pressure transmitter, they have a PLC in the machine, they can make the control, you can make the changes for the turnover rough to fine vacuum from the display of the machine. But nevertheless, we can do it. Okay, to a central vacuum supply, we can connect thermoformers, chamber machines. Also possible is to connect other food processing machines, like a vacuum tumbler. A vacuum tumbler for molding, for tumbling the meat. There we need vacuum. Normally pressure of 200 millibar is required. Can also be connected to a centralized vacuum system. The same is for sausage fillers, for cutters, for handling machines. Every machine which needs vacuum in a food processing plant may be connected to one centralized system. But nevertheless, the repay of the costs will be realized with the packing machines. Because once again, for the packing machine, I increase the performance and I decrease the power consumption for vacuum generation. So therefore, this investment will be repaid. You will see later on an example. It will be repaid very fast. I can't make this calculation for a vacuum tumbler. A vacuum tumbler has a working time, let's say, between 8 and 12 hours. It will not become 1 minute faster with the centralized vacuum system. For a sausage filler, in a sausage filler, there's a small vacuum pump, 40 cubic meter power is built in. I will not save any energy with this small pump. So the only reason for connecting production machines to centralized vacuum system is the hygienic aspect. And the aspect, if a pump fails, that you have a standby pump. But the return of investment is within the packing machines. Once again, the thermoformer, we have the forming station, the sealing chamber. Let's have a look to the forming station. And normally you can say, okay, this is the easiest part for the centralized vacuum system. Because just one single stage expansion, only pressure 150 millibar, it's not a big problem. The problem is the packing machine, because there are a lot of different types for the forming of foil. In the packing machine, the bottom wrap is transported into the forming station, and now the foil has to be warmed up, because you can't form a cold foil. And now there are different possibilities, different ways to heat up the foil. You can have a heating plate in front of the forming station, or you can have the heating plate on top of the forming station. That is to say, in the first station, the foil is sucked to a heating plate, is warmed up. In the next step, the foil goes into the forming station, sucked from the bottom, and the mold is formed. This is the so-called preheating. Or you have the heating plate on top of the mold. So therefore, the foil is sucked up to the heating plate and afterwards sucked down. or it is not sucked up to the heating plate, it is pressed up to the heating plate with compressed air. And then afterwards, it is sucked down. And if you have this, once again, two possibilities. Fill up with compressed air up to 2 bar, press the foil to the heating plate, and connect directly to the vacuum pump, or release the atmospheric pressure and then connect to the vacuum pump. So there are a lot of different types of heating of the foil, and there's a big difference in the load for the central vacuum system and the vacuum demand, depending only on the way of heating up the foil. So first, if you have no preheating, then we have the heating on top of the form. Then we have a top heating. If we have a preheating, it could be a single heating plate, or it could be a sandwich heating with a heating plate on top and above the foil. This is sandwich heating. Or we have, if we have the heating plate on top of the form, we can have a standard release, or we may have a quick release. That is to say, first release. And this is very important, because if you do not have a quick release and you have the forming station filled up with 2 bar, it's the double of the volume you have to evacuate if you go directly to the vacuum line. And this makes a big difference for a centralized system. So that is to say, I need a lot of information about the packing machine. Next is the sealing station. You have talked about this. We are making this, the evacuation to reduce the number of oxygen particles. After the evacuation, I can make a vacuum package, seal the package, and finished. Or I can regas, make a modified atmosphere package, regas, seal afterwards. Or also possible is to make a gas flush. Gas flush means I evacuate, let's say 200 millibar, then I open the vacuum to the gas, and I'm sucking the gas through the package. There are a lot of products which need such a gas flush because it's not possible to evacuate them to a very low pressure. Like there are some fresh sausages. Right? Yeah. Okay, this is the most important point. And for the calculation, I need to know the size of the chamber. That is to say, the index length, the width, the maximum depth of the package. And today, a lot of packing machines, they are equipped with an automatic adjust of the depth of the machine. That is to say, if you change your product, let me say in the morning you're making flat packages of 20 millimeters. In the evening hours, you're making packages with 100 millimeter. Normally, you open the sealing station, put in plates or remove plates, and the same in the forming station. Or today, there are a lot of machines with an automatic adjust. They are moving a table up and down. The problem is, with the automatic adjust of the depths, I have to evacuate the whole chamber within the empty space under the table. That means a lot of volume. We need more pumping speed, but nevertheless, for the machine becomes faster if you have a lot of changes of the depths. So that's what I have explained before, the automatic drawer depth adjustment. It is very useful if a customer has a lot of changes in his product over the day. So that is to say, if you have to change the depth of your package 8 times a day, then it makes sense to have a machine with an automatic adjust. If you are changing the depth once a week, maybe you have to think about if it is really necessary, because you need a lot of pumping speed, a lot of vacuum for this automatic adjust of the depths.
So just a question. So what kind of machines make sense to put together in a centralization in the same ring or in the same pipe?
Yeah, also a very good question. First of all, we can connect every type of packing machine from every manufacturer. It makes no difference if it is a machine from the manufacturer A or B or C or D. Makes no difference. Next point, we have some customers, some big meat processing plants with more than one centralized system. They have 2 or 3 vacuum centers. Normally, it is better to connect more machines to one system. That is to say, as bigger the vacuum system, as cheaper is the system. On the other hand, if there is a big meat processing plant, they have 2 packing areas, and between this there is 100 or 2 meters distance, then we have to check if it is possible to build a pipe net over this long distance. From the physical viewpoint, the distance between the centralized vacuum system and the packing machines makes no difference. That is to say, we can pack your products here in Spain, and we can install the central vacuum supply in my company in Germany, if we will find anybody who can build a pipe net. So the question is only, is it possible to build a pipe net? And so back to the question, it is better as more machines, to connect more and more machines to a centralized system.
Probably you are going to explain it afterwards, but what about the oxygen version or this kind of modified atmospheres?
For regassing with oxygen? Yeah. Yes. That is a problem. It's not a problem, but you have to be aware, if you are making modified atmosphere packages under oxygen, then you need, in most cases, you need special vacuum pumps. The problem is, normally the sealing chamber is evacuated down to final pressure, vacuum valve is closed, then open the gas valve and flushing with oxygen. So no oxygen may come into the vacuum pipe. But if there is a broken valve, if there is a damage in the machine and the vacuum valve is opened, then you will get oxygen into the vacuum pump. If you have an oil lubricated vacuum pump with hot oil and you have oxygen, the pump may explode. I don't think it will explode, but it will burn. And it will burn. I have seen a lot of pumps which burned down. I have made a lot of reports concerning these pumps for insurance companies that they burned due to oxygen which comes into the pump. So that is to say, if the machine cannot avoid that oxygen come into the pump, then you need a special oxygen pump. That means special oil, special filters, and most of all, an exhaust pipe. I have seen very often that there are, in a meat processing plant, there's a packing machine, regassing with oxygen. Beside the machine, a vacuum pump, red painted vacuum pump, special for oxygen, perfect. But the outlet of the pump is in the room. So the pump, the oxygen is going through the pump and in the packing room. And that's dangerous. It's not allowed, not at all. So therefore, if you have an oxygen pump, please be aware you need an exhaust pipe from the exhaust from the pump out of the building. Very important. So this is for the machine which cannot avoid that oxygen comes to the pump. There are some manufacturers of packing machines, they have a special safety system which avoid that oxygen may come into the pump. And these machines can produce MIP under oxygen with normal pumps.
This is what you have explained. It's only valid for the oil lubricated pumps or also for the rotary blow pumps. Do you need a special pump to transport oxygen?
Yes, yes. You always need a special pump And it's depending on the local authorities and the laws. I don't know the laws in Spain, but I know in Germany, each pump which may pump oxygen has to be tested. Both. Nevertheless, if it is a dry running pump or whatever, each pump has to be tested and has to be signed. This pump is may be used for oxygen. But I think it's all over Europe. We talked about the packing machines. Now let's make an example. We have an inline thermoformer. The machine is running with 6 cycles per minute. That means we have 10 seconds time for each cycle. One cycle, that means transport of the foil into the machine, closing the chamber, the sealing chamber and the forming station, evacuation, sealing, ventilation of the chamber, and opening. And then the next cycle starts. For this example, we have 10 seconds per cycle. Let's say we need 2 seconds for the transport of the foil and for the closing of the chamber. We have 6 seconds for the evacuation and 2 seconds for sealing and ventilation and opening of the chamber. Now we want to increase the performance from 6 cycles to 8 cycles per minute. That means we have to save 2.5 seconds because now we only have 7.5 seconds per cycle. So that means we have to evacuate very fast so that we are saving 2.5 seconds per cycle. That is to say, instead of 6 seconds, we only have 3.5 seconds for the evacuation. And this is, with the centralized vacuum system, no problem, not at all. The 6 seconds we will reach with a normal vacuum pump, rotary vane pump, 300 cubic meter per hour in the machine. The fast evacuation One second. So this is the normal, the integrated vacuum pumps, a rotary vane pump for the forming station, rotary vane pump for the sealing chamber, or a combination of a rotary vane pump and a booster pump directly integrated in the machine or installed beside the machine. The disadvantages we have discussed before: the heat into the cooled area, the negative energy balance, because we need a lot of energy for recool the heat up in the room, and we have to stop the machine if the pump fails. Yes, please.
Okay, so sorry, it's just a little question. I have a customer that put in the forming area a side channel pump. It makes sense with a special protection and so on, but a side channel.
Yeah, a side channel blower. Normally, the final pressure of a side channel blower is maximum, let me say, 300, 400 millibar. So this is only usable if you have a very thin film. But I think in most cases, you need a pressure lower than 200 millibar, 150 millibar for the forming. So it's possible, but I do not know. I'm not sure if I know any customer who is using side channel blower for the forming station. So, and we have the problem, if the pump fails, we have to stop the whole packing line. So therefore, we install the centralized vacuum system, which is connected with a pipe net, and to the pipe net are all packing machines connected. And the same with the forming station. Now we have no heat in the production area, the fastest possible evacuation, And no problem if a vacuum pump fails, the standby pump is fully automatically turned on. Sorry. So let's make an example. We have a company, it's called the Oktoberfest Sausage Company. They're making special sausages for the German Oktoberfest. This company has some packing machine, one inline thermoformer from GEA, 3 multivac inline thermoformer, and 1 Weber-Matic chamber machine. And this customer is interested in a central vacuum supply. First of all, I need some information about the packing machines. That is, first of all, I need to know the size of the sealing chamber. That is to say, it is the index length of the machine, it is the width of the foil, and it is the maximum forming depth, depending on the product of the customer. I need to know the filling level. That is to say, how much of the package is filled with product. Is it 10%, or is it 20%, or is it 50%? By the way, does it make sense to have a package with 20% of the volume filled with product? No, because there's one big problem, and I think maybe not everybody is aware of this problem. What happens if you have a small product in a big package? This is the bottom film. The bottom film is formed, and let's say we have a volume. This volume, let's say, is 10 liters. Now, we put in the product, only one sausage. The volume of the sausage is 1 liter. This is in the sealing chamber, the top film. The package, the sealing chamber is evacuated. Final pressure, very good final pressure, 2 millibar, 2 millibar. Now we seal. The upper foil and the bottom foil are sealed together. Now, sealing ended. Now we are releasing the chamber. What will happen with releasing of the chamber? The foil is pressed on the product like this. So we have reduced the volume from 10 liters to 1 liter. What will happen with the pressure? It is the so-called law of Boyle and Marriott. And this law says, in a closed system, the product of the pressure and the volume is always constant. We have a closed package from 10 liter, which is pressed to 2 liters. So the pressure will rise up from 1 millibar to 10 millibar. And that's a problem. And therefore, you have to adapt your package to your product. This is very important due to this problem. Okay, sorry for the sidewalk. Let's go again back here. So I need to know the filling level because the volume which has to be evacuated is the volume of the sealing chamber minus the volume of the product. Therefore, I will have the volume. I need to know the final pressure. I need to know the pumps you have and the current speed of the machines. I have the chamber machine with the volume, the pump, rotary vane pump, U5.200, and the performance 1.8 cycles per minute. Of course, for the chamber machine is no forming of foil. For the thermoformers, I need to know what kind of forming station, what kind of heating of the foil. So, and now the customer wants to remove the pump and he wants to increase the performance. I want to increase his production. So the option one is, if you need to increase his production, install more packaging machine, further packing machine. Or option two, increase the performance of the existing machines. That is to say, to achieve the higher cycle rate, option one, install further packing machine. That means higher production, higher cycle rate. Oh, sorry, I've been too fast. For the installing a further packing machine, he can increase his production without any problem. By installing a central vacuum supply, he can increase the production. And furthermore, he can decrease the energy costs. The operating costs, he has a backup pump, and the hygienic aspect. No more pump in the packing room. So I think the advantages of option two, increasing the performance of the machine by using a centralized vacuum system, are very impressive. Disadvantages, if you install more packing machines, the cost for the additional machines. Increase energy costs, and so on. With the central vacuum supply, disadvantage, it's only the cost for the central vacuum supply. So, what I need for the calculation, if I want to make the first rough calculation of a centralized vacuum system, I need some information concerning the packing machines. For these informations, we have an inquiry. You see here, for the inline thermoformer, I need to know the index length of the machine, the width of the foil, the maximum depth. I need to know what kind of product you are packing. How many % of the packages are filled with product? I need to know what is the performance you're running today. What do you want? How fast shall the machine be? And I need to know what kind of heating for the forming of foil is adapted at the packing machines. Yes, please.
Thank you. If we know the brand of the packaging machine and the model, all the rest of details, you can know it?
No, unfortunately not. Because the type of the machine, the manufacturer and the type, in this example here, Multivac and R520, this is only the model of the packing machine. But for each packing machine, they have different tools in the machine with different index lengths, widths, and so on. So therefore, I need to have all this information. A lot of customers have these informations without any problem. They have in their papers, they do exactly know what kind of machines. If the customer does not have this information, or it is not easy to get this information, it is no problem for us to check this on site. So that is to say, we will visit the customer, we will have a look to the packing machine, we can check the size of the machine, the size of the chamber, we can check the performance today, the evacuation time, and so we may get all necessary or required informations for the calculation. Sometimes for packing machines, example is if the machine is adapted with an automatic adjust of the depth, then I need the help from the manufacturer of the machine. But this is no problem. If I know the type of the machine and the serial number, I will contact the manufacturer of the machine and I will ask every detail I need to know. And with all these informations, I can calculate the central vacuum supply. And besides the information about the packing machine, I also want to know what vacuum pumps the customer has today. Because we do not want to sell new pumps now. We want to build a central vacuum supply. And first of all, we try to use your existing pumps. Maybe there are a lot of pumps which may be very easy integrated in the central vacuum supply. Sometimes there are pumps, if a pump is too small. Let's say if I have a vacuum pump, 100 cubic meter per hour. It makes not a big sense to install this pump in a central vacuum supply because the cost for a stand, valve, and so on, this is too expensive. Makes no sense. But sometimes the customer has some pumps which may be used. They can be used. We need some more pumps. Most times we need booster pumps. But together with the existing pumps, we can install the centralized system.
Sorry, another question.
Yes, please.
Yeah. To use the existing pumps, there is a brand or there is a model that is not possible to integrate in a central system?
No.
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 Okay.
I do not know. There are some old pumps. There are some old bush pumps, double stage pumps, which are not very easy to install. Make no sense. But most types of pumps may be used.
And by the way, there is some packaging machine. There is any packaging machine, any brand of packaging machines that are not be able to take part in the centralization?
No, 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 not at all. Okay, on the basis of this information, I have calculated the central vacuum supply. We have the auxiliary vacuum. The pressure will be between 60 and 115 millibar. Once again, this maximum 150 millibar, we will have the maximum pressure if all connected packing machines are evacuating exactly the same time. We need a pipe with a diameter of 200 millimeters, 30 meters long. We need an additional buffer. Sometimes I need additional volume, I need tanks. If the machinery room with the central station is nearby the packing area, and in this example, I only have a pipe net of 30 meters, I do not have enough volume in the pipes, and therefore I need additional tanks. But this is not a problem to install the tanks. But if the pipe net is longer, maybe I do not need tanks. In this example, for auxiliary vacuum, we need a 1 cubic meter tank, and we have 2 rotary vane pumps, 300 cubic meter per hour for the auxiliary vacuum. Rough vacuum, the pressure between 10 and let's say 60 millibar. We have 2 pumps, rotary vane pumps, 300 cubic meter, and 1 booster pump, and a 2 cubic meter tank. For fine vacuum level between 1 and 3 millibar, we need 2 booster pumps, 500, 1000 cubic meter per hour. This is a flow chart of the system. We have the auxiliary vacuum, 2 rotary vane pumps, 1 buffer, and here are the packing machines connected. We have the rough vacuum, 1 booster pump compressing to a packing vacuum, which is evacuated by 2 rotary vane pumps, 300 cubic meter per hour. And we have the 2 booster pumps in fine vacuum. And here we have 1 pump only for backup, only if a vacuum pump fails. If a vacuum pump fails here, this pump is automatically turned on for auxiliary vacuum. Or it is turned on for backing vacuum. If the pump in rough vacuum fails, the 3 pumps here are running together for rough vacuum. If one of the fine vacuum pumps fails, this pump is running for fine vacuum, and again, the 3 backing pumps for rough vacuum. So we have a fully automatic turnover to standby if a vacuum pump fails. And the backing pump is necessary in a central vacuum supply. Before, with the integrated pumps, for these machines, this customer we had a lot of pumps in use, 2 times 70 cubic meter, 2 times 100 cubic meter, and so on. With the central station, we only have 4 rotary vane pumps, 300 cubic meter per hour, 3 booster, and 1 for standby. That is to say, with the individual pump, we had 37.9 kilowatt energy consumption. With central station, only 32.2 kilowatt. That's to say, less installed power for vacuum generation within a higher cycle performance of the packing machines. So that is to say, I do not need more pumps. Normally, I need less pumps than before because the pumps are better used, what I've explained before. So we have the packing machines in the white area of the production room in the hygienic area. We have a pipe net, 3 big pipes, 200 millimeter, which are from the packing room built up to the central vacuum station. We have the 2 pumps for auxiliary vacuum, 1 booster with 2 packing pumps for rough vacuum, for fine vacuum. I have additional tanks and the standby pump. Control cabinet. Once again, the number of machines with the cycles, and we have increased the performance. For line number 1, the multivac from 9.1 cycles to 10.5 cycles per minute, only by faster evacuation. I can't give you any number how fast a packing machine will be by connecting it to a central vacuum supply. It is depending on the type of the machine. Let's say if you have a packing machine, you are making flat packages, 20 millimeters for sliced sausage. You have a very small volume of the sealing chamber, and you have a very big vacuum pump installed in the machine. The machine, the evacuation is very fast because you have a big pump and a small volume. Maybe I can save 0.1, 0.2 seconds, but not more. If you have a big package, a big volume of the machine, and the pump is 3 meters beside the machine, then I can increase the performance. But nevertheless, for the big machine, I increase the performance. For the small machine, I decrease the power consumption. But for each machine, I have to calculate what is possible. So in this example, the increase in cycle performance is between 15 and nearly 40%. It is for the big trimmer machine from Webermatic, sorry. Normally, for the big trimmer machines, it is always possible to increase the performance. So that is to say, the average increase in performance is 22.7%. Now, it is not possible to use the faster machines all over the day because sometimes you have no product. You have to change the foil, anything. You have always to stop the machine again, to start again. So let's say we can use 15%, 50% more performance of the machine are usable with a centralized vacuum system. Let's say you are packing 12 hours per day, 240 days per year, staff per machine, 3 workers. And it's not only for the packing machine, it is for the whole line. That is to say, maybe there's a slicer in front of the machine. You need 1 worker for the slicer. You need 2 for the packing machine itself. You need 1 for the packer afterwards. So you have to calculate for the whole line. So I think this is not a lot of workers for the whole line. Let's say 3 workers. The cost for the workers are 15 euros per hour, and cost for the machine, that is to say for power, for gas, for compressed air, let us say 5 euros per hour. Now, with the increase of the performance of the machine, we will save the time, and we will save 1.5 hours per day caused by the faster packing machines. And that means we save 1.5 hours per day, cost for the workers 16,200 euros, for the machine 1,800, means 18,000 euros per machine. This example, for 5 packing machines, we are saving 90,000 euros per year, caused by the faster production. Next point is the power consumption. We are saving energy. In this example, with the individual pumps, 12 hours per day with 63.9 kilowatt. With the central vacuum supply, we only running 10.5 hours per day and only 36.2 kilowatt. That is to say, we are saving 9,200 euros for energy. This is calculated with the energy with a cost of 10 euro cent per kilowatt hour. That means we are saving 90,000 euro by increasing production, saving energy. We are saving operating costs because you do not need to stop the machine for maintenance and so on. It's a total saving per year of 100,000 euro. That means the investment of 120,000 euro is repaid after 14 months. And this is what I've told you before. Central vacuum supply for packing machines will be repaid in a very short period. And from my experience, the repaid time, the time for till it is repaid is between 6 and 20 months. Only by saving energy and increasing production. And beside this, you have the hygienic aspect. Yes, please.
From how many machines would you recommend to install this centralized pump vacuum?
It is also possible to make it for one machine. This is the so-called combined system. This is also the first way, or the first chance to build a central vacuum supply. For one packing machine, the repaid time will not be very short, of course. But if your customer has 2 or 3 or more machines, I think it makes sense to install a central vacuum supply. And if the customer has 5 or more packing machines, let me say, he needs a central vacuum supply as in the same way as he needs the daily bread.
Okay, what happened when the customer puts the pumps, all the pumps, 30 meters far from the packaging area?
Then the machines may become much faster. Because today, if the distance between the vacuum pump and the machine is 30 or 40 meters, he needs a long time for evacuation, or he has very big pumps,
And with the
as you have seen before. And then with the central vacuum supply, you save pumps and you make the machines much faster. Then frequently asked questions. What happens in the centralized vacuum supply if the vacuum pump fails? Nothing. No effect on your production. The standby pump is switched on fully automatically. It is not 1 second without production. And then you have time enough. You have in the packing room, you will have a sign, a red light, or anything else in the packing room to show, okay, something wrong in central vacuum supply. send the technician to the machinery room. He can check, okay, a pump is failed, I can repair, I have to remove or replace or anything else. But it's time enough because no effect on the production. What happens if the operation terminal fails? That's a problem. We have a big operation panel in the enclosure. There you can turn on and off the station. You can say, okay, I want to make repair work at pump number 3. Press pump number 3, turn off. The pump is turned off. The standby pump is fully automatically switched on, and you can make the maintenance work. If there is a failure at the pump, you can see on the panel, okay, it's the problem is oil temperature at pump number 6 or anything else. If this operating terminal fails, the central vacuum supply is still running in automatic mode without the panel, without any problem. But now, let me say we have one pump was set into repair work to stop for repair, and now the terminal fails. You have no chance to put it again in normal operation. Therefore, you open the enclosure. There are two switches. You have to press the same time for 5 seconds, and all is set again back to normal mode. So that is to say, it is running in automatic mode also without the terminal in the enclosure, without any problems. What happens if the PLC fails? That's a problem. If the PLC fails, the station is stopped. You have stopped all your packing machines, the whole packing area, each machine has to be stopped. You have to go to central vacuum supply. You see, okay, PLC failed. You open the enclosure, you open a cover, and under this cover, we have a switch for each vacuum pump. And you can turn on each vacuum pump in a manual mode. And after 5 minutes, central vacuum supply is running again. That is to say, in our enclosure, we can remove the PLC. We can remove it from the enclosure. We can start the pump by manual mode, and you can run. Just to be absolutely sure to save your production. So within, let's say, 5 or 10 minutes, central vacuum system is running again. You can start your packing machine. The same, by the way, the same is if the DC power supply fails. Exactly the same. You open the enclosure. There's one key you turn on, and every important part in the enclosure is turned from DC supply to AC supply. And then you can turn on each pump to run it in manual mode. And we are a little bit proud. We have, over the last 40 years, we have built more than 350 big central vacuum supplies, and only 2 stations failed. And they had to stop the production for a longer time. One, a meat processing plant in Belgium, the packing room was burned down. Second, a meat processing plant in Germany, the whole machinery room was burned down. But these are only 2 times that our central vacuum supply failed totally. And the burning was not caused by our central station.
Thank you very much. I have another question. When you compare, in order to calculate how many time I need to recover the investment that invest, when you make these calculations, you are thinking about with the integrated pumps, the pumps are running all without any break or without any problem. But this normally this don't happen. Normally the pumps have problems and some water inside and some problems. Okay, you have to repair one. You have an stop.
Yeah, but you have with the centralized vacuum system, you have less problem than before. Yeah. Because first time, you have less load on the vacuum pumps, what I've explained before, because they are running on a mean level all the time over, point 1. Point 2, if there is a problem, you can do the maintenance or the repair work during the normal working hours.
Now imagine I am the manager of a plant production, and I'm thinking about to make a centralization because I have all the integrated pumps. I have 4, 5, 6 packaging machines, or I have centralization, but I have all the routes inside the cleaning rooms and so on. What I have to do? I have to call someone, or I have to what is the next step, the first step that I have to?
The first step is that you will have a contact to Becker in Spain. First of all, call your sales guy from Becker and tell him, okay, maybe I'm interested in a central vacuum supply. He will provide you with the inquiry concerning your packing machines. And if you feel able to fill up this inquiry as far as possible, you may send back, and we will calculate the central vacuum supply. We will see if you need a combined system with booster in the machines, or if you need a totalized central station. Maybe we have 2 or 3 different ideas. We will make a rough calculation about cost and benefits. And with this, we will visit you. We will show you, okay, these are our ideas. It will be a cost approximately this and this. You will save this and this. And if you are still interested, and I'm sure you're still interested, we will visit your plant. We will check the machines again ourselves. We will discuss where can we install the central vacuum supply, where do we have a room, where you have space. And afterwards, we will provide you with a detailed offer of a central vacuum supply. If you tell me, okay, the first step, fill up the inquiry. I don't know, I'm not sure what to fill up, I have no time. No problem. We will visit you. We will check the machines. We will go to your packing room. We need to have a look to each machine. We may make some tests, some measuring at the machines. You do not need to stop the machine for this. We will check the pumps, and we will provide you with an offer.
Okay, yes, but I need to produce every day from Monday to Friday. Is possible to do it on weekends?
Yes, of course. I'm doing this job very long, and I can't remember that we have ever met a customer who told us, no problem, we can stop production for 1 week, 2 weeks, no problem, you have time enough to install. Now, normally, if we are lucky, the customer will stop production Friday at 12 o'clock. We will go there, we will remove all the vacuum pumps from the packing machines. We will install them in a machinery room. We will set the vacuum system into operation. We will make the modification at the packing machines. And Monday morning, 6 o'clock, he may start his machines. Besides this, it is also possible that the customer is doing some part itself. Example, let's say the pipe net. We need a pipe net. We need thick, very big pipes, 2 or 3 pipes from the machinery room to the packing area. Most times we use PVC for the pipe because it's a cheap material and it's easy to handle. It is not necessary that we send 4, 5, or 6 workers from Germany to Spain to build a pipe net. Makes no sense. So I will design the pipe net. I will define what diameter at which point. I will make a drawing. The customer can make the pipe net himself, or there is a local plumber who can make this pipe net without any problem. So let's say in our example, customer wants to have central vacuum supply. I make the design of the pipe net, and he will build the pipe net. Pipe net is finished. Then afterwards, then we come Friday, we move the pumps, connect to the pipe net, and so on. The modification of the packing machines can be done by the manufacturer of the machine, what I've described before, or we can do it. If the customer says, okay, I have a big plant and I have 8 or 10 technicians which are working here, and we can do it ourselves. No problem. We will provide the customer with all necessary drawings, and he can build himself. He can build up the pumps on stands. He will get from us every necessary parts to connect the pumps to the pipe net, and he can make all this himself. Maybe he needs one engineer from us to set it in operation, but everything is possible. We are open. We are absolutely open. But most important point, the installation will be done at a weekend. You do not have to stop the production. We need 2 days without production, and that's enough.
Okay, is there any problem with PVC?
No, there's no problem, not at all, no electrostatic problem with PVC. PVC is, on the one hand, it's a very good material because it is no problem for contact with food, because you can eat PVC without any problem for your body. Yes, it is, really. No details, but what goes in comes out. The own problem is if PVC burns, then it is a big problem. So we have some customers who wanted to have the whole pipe net in stainless steel. Of course, it's possible. It's just the costs. We have one big customer. They have built the pipe net themselves. The length of the pipe net was 150 meters. 3 pipes, diameter 400 millimeters, 150 meter long. They made it completely in stainless steel. This was a customer in the Kingdom of Saudi Arabia.
Okay, I have another question. Sometimes I have lots of problems with water because at the end of the journey we clean the machines with water and some chemical products, and sometimes one worker forget to open and to take out the water before start working. What happened now? I have to change the oil and to wash all the pump. What happened when it happens with the centralization?
Normally, it is a problem, and I know it because sometimes they will forget to close the chamber before cleaning. You can put each packing machine in a cleaning position, so all chambers are closed. They forget, then they are cleaning the chamber. Oh, it's wet. Easiest way is close, vacuum. Oh, it's clean. Yes, I know this. It is not a big problem because the water goes into WAF vacuum. In WAF vacuum, at 50-60 millibar, we have no problem with the water. It will stay in the pipe, it will freeze, maybe, but it's not a big problem. If it is too much water, then from time by time, you have to fill a hole in the pipe to let the water out. So normally, it's not a big problem. But if it happens very often, or if you are packing products under liquid, we advise to install a condenser at each packing machine. It's also the same if you have products which are with spices. And during the fast evacuation, the spices will go up into the pipe. Nothing happens in the pipe, but it makes no sense. So therefore, for these machines, depending on the product, we install in front of the machine filters or condensers. The question was if it makes sense to make the centralization only for the oil-lubricated rotary vane pumps and to leave the booster pumps in the machine. This is only depending on the number of machines. The best way is to have all the pumps out of the room. The hygienic aspect, not so important because the booster pump is dry running. Energy aspect, not so important because the booster pump in the machine will not become warm. But if the booster pump fails, then you have to stop the machine again. So from safety reason, it is better to have all the pump out because then you have automatically turn over to standby if a pump fails. But the most important point is only the number of machines. If you have, once again, more than 3, 4 packing machines, it makes no sense to leave the booster in the machine, because for each new machine you will add, you always need a booster again. It's possible, but it makes no sense.
Okay, and what about the maintenance? It's easy to make maintenance operations in a central system.
Yes, this is one of the big advantages of the centralized system, because you can do the maintenance work at the pumps during the normal working hours. It is very easy. You go to the enclosure, to the terminal, and you say, okay, pump number 3, you press pump number 3, turn off. The pump is turned off. You will get an information. Please open the enclosure and turn off the terminal block and avoid that it will be turned on again. The standby pump is fully automatically switched on, and then you can make the maintenance work at the pump. Afterwards, you go, okay, pump number 3, finished, run again, and standby pump is turned off, and it's in normal mode. And then you can make the maintenance work one pump after another. There are no special additional maintenance which is required at the central vacuum system. We only have the vacuum pumps. We have electropneumatic valves. Okay, sometimes you have to check if they are working. And that's it. We have a pressure transmitter, and that's all.
And what happens if we can increase my production to, if I sell 2 more machines, or I want to make another plan or to make bigger my plan?
Yes, this is absolute easy, because the central vacuum supply is constructed, is built up in blocks. That is to say, I'm not sure if I have some picture. Maybe let's have a look to a picture. This is a very small central vacuum supply. Here we have 2 vacuum pumps for auxiliary vacuum, 2 vacuum pumps and a booster pump for rough vacuum. The fine vacuum is not shown on the picture, and 1 standby pump. If the customer now wants to increase production, that is to say he bought a new packing machine, or he removed the packing machine and installed a bigger machine, longer index lengths, higher performance, anything else, I will make a recalculation, and maybe I tell him, okay, auxiliary vacuum, no problem. The pressure rises from mean value 100 to 110 millibar, no problem. Rough vacuum, at the end, we have to add a pump. No problem. We can add a pump here, or we can add a pump here. The same in fine vacuum. So that is to say, I calculate, and then I tell him, okay, we have to increase, and we add more pumps. If I need more volume, I can add tanks. Because if I have more machines, sometimes I need more buffer volume. Okay, then we install additional tanks. If he is building a new packing room, and we have to mount more pipes to get to the new room, we have more volume. Problem is the diameter of the pipe. Because if the diameter is too small, we have to remove the pipe. And that makes no sense. And therefore, if I calculate the central vacuum supply, I will have enough space in the diameter of the pipe. Because today, if 100 millimeter is enough, I will use 160 millimeters just to have enough reserve for later increase of production. Because it makes no sense to remove the pipes. And the difference in the price from 100 to 160 millimeters is not so high. And also, if you increase the central station in the electric enclosure, I have minimum 40% free space in the enclosure. Because over the last 14 years, I don't know if there is one customer which never increased his production. Every central station will be increased over the years. Maybe let's have a look to some pictures of centralized system. This is a small system, very small system. This is a bigger system. There we have connected 40 inline thermoformers. This is the biggest installation we ever made. This is a meat processing plant from the company Rewe in Austria. Rewe had decided to close all the meat processing plants and build one centralized new plant. And this is the biggest station we ever made. Here you see the station, you see the enclosure with the terminal here. There we have the flow diagram, the flow chart is on the enclosure. Here you see the enclosure, here you can see here the plate. And we have here lamps for each vacuum pump, which are green or red. So you can see if the pumps are running. And most of all, also if the PLC fails or the terminal fails, you have a chance to see what happened at the central station, which pump is running. And then it's very easy to open the door and to turn on. Here you see, here under this cover, here are the manual switch. So it can turn on each pump by manual, without PLC and without DC power supply. The pipe net, here you can see pipes in PVC can be installed outside of the building, inside the building. Then we have small branch tubes. The big pipes are here under the ceiling. Then we have small branch tubes down to the machine, ball valves, and then a flexible hose, normally in PVC, or also possible flexible hose in stainless steel. These are pipes. This is a meat processing plant in Switzerland. They wanted to have stainless steel in the production area, also possible. This is the connection at the machine, rough and fine vacuum with flexible hoses in stainless steel. And this is a special valve plug for multivac. This is not our block. This is the block from multivac. Here again, the big pipes in stainless steel, branch tubes in stainless steel, everything is possible. It's depending on the customer. Today, most customers, they have a border over the packing machines between black area and white area. And the best way is to have the big vacuum pipes in the black area, in the not hygienic area, then branch tubes at the wall down in PVC, and then into the white area under the machine in stainless steel. This is the absolute hygienic version. And everything is possible, only depending on the demands of the customer.
So thank you very much for
Welcome.
sharing with us just a piece of your knowledge about this. I think this is amazing for us to understand how it works. Thank you very much.
Thank you.
Bueno, queremos darle las gracias a Mr. Bills por compartir con nosotros un poco de su conocimiento acerca de, creo que hemos entendido un poco mejor cómo funciona y qué es realmente una centralización de vacío, que no es solamente alejar las bombas, que también de la zona de producción, no solamente tenerlas lejos, sino además podemos conseguir estas tres grandes ideas que Mr. Bills ha compartido con nosotros. Una es mejorar la producción, aumentar la producción, conseguir más ciclos por minuto con las mismas máquinas, con los mismos operarios y por lo tanto ganar dinero, productividad, es la palabra mágica. En la segunda idea sería esta de ahorrar, perdón, ser más eficiente, es decir, con menos energía conseguir más. Y esto es, primero, por no tener que refrigerar en exceso, quitando las bombas de dentro, todas las bombas, también los roots, quitándolas de las zonas refrigeradas, nos evitamos tener que aumentar la capacidad de refrigeración y además vamos a usar las bombas de una manera más eficiente y por tanto vamos a ahorrar energía y eso hoy en día sabemos que es mucho dinero. Y en tercer lugar, y no sé si ha quedado suficientemente claro, vamos a tener bombas redundantes, es decir, vamos a poder trabajar 24/7, constantemente. No importa si tenemos que hacer mantenimiento, si tenemos una avería de una bomba puntual, vamos a tener una bomba que ocupe su lugar y lo vamos a conseguir de una manera más inteligente, esta manera clever de hacer las cosas. Por lo tanto, muchísimas gracias. Creo que todos hemos entendido. Si alguien tiene alguna pregunta más, no soy yo a quien hacérsela, teniendo aquí a Mr. Bills, pero nada más. Quiero agradecer a todo el mundo, tanto la presencia aquí como la presencia en streaming. Ha sido un verdadero placer para nosotros poder organizar esta sesión. Esperamos que haya algunas más y vamos a pelear para que sean tan interesantes como esta. Y por supuesto esperamos vuestros comentarios, preguntas, cuestiones. Vamos a estar en contacto y vamos a hacer que esto sea el principio de una gran relación. Muchas gracias otra vez y buenas tardes.